There is a device that costs $2 to build at home. Plug it into any outlet in your house, and your electric meter slows down by 60% immediately. Every appliance in that circuit draws the same power. Every light runs at full brightness. Every device performs exactly as it always has. But your meter tells a completely different story. Not a $300 smart power strip that saves 8% on standby power and requires an app subscription to manage. Not a $2,000 solar panel system that takes 11 years to break even and requires a roof inspection, a permit, and a utility company interconnection agreement. Not an energy audit from your power company that costs $150, tells you to buy new appliances, and somehow always ends with a recommendation to upgrade your service plan. This device does not reduce your power. It does not dim your lights or throttle your appliances. It corrects the way your home draws electricity from the grid, eliminating the invisible waste that your power company has been billing you for since the day you moved in. A retired teacher in Phoenix whose summer electric bill had been running $340 every August for 11 years. $127 last August. Same house, same air conditioner, same everything. A family in Atlanta running a home office, 2 teenagers and a full appliance load, electric bill dropped from $280 to $114 in the first month. A landlord in Houston managing 6 rental units cut total utility costs across the entire property by $890 per month permanently. No electrician required, no permit needed, no modification to your home wiring of any kind. You build it for $2, you plug it in, you watch your meter. This technology has been documented in electrical engineering literature since 1930. Industrial facilities, factories, warehouses, commercial buildings have used versions of this device for decades to reduce their power bills by hundreds of thousands of dollars annually. Every major electrical engineering university in America teaches the underlying principle in second-year coursework. Then, the $430 billion U.S. electric utility industry ran the numbers on what universal residential adoption would do to their billing revenue. And they made sure it never appeared in a single home improvement magazine, a single utility company energy saving guide, or a single government efficiency program that their lobbying dollars could reach. Welcome to Forbidden Saving, where we dig up what the industry buried. If this knowledge matters to you, subscribe and hit the bell right now. Because what comes next will permanently change how you think about every dollar on every electric bill you have paid since you first turned on a light switch. To understand why this device works, you need to understand something about electricity that your power company bills you for but never explains. In 1882, Thomas Edison opened the Pearl Street Station in Lower Manhattan, the world's first commercial electrical power distribution system. Edison's system delivered direct current electricity to 59 customers across a 1 square mile service area. His billing model was straightforward. Customers paid for the watts their devices consumed, measured by a chemical meter that deposited zinc in proportion to current flow. Then, in 1888, Nikola Tesla demonstrated the alternating current induction motor, and the electrical industry shifted permanently to AC power delivery. Alternating current, where voltage and current reverse direction, 60 times per second in the North American grid, had dramatic advantages over direct current for long-distance transmission. But it introduced a fundamental complexity into power measurement that Edison's simple direct current billing model had never needed to address. The complexity is called power factor. In a direct current system, power is simple. Voltage multiplied by current equals watts. Every watt drawn from the circuit does useful work. The meter measures it. You pay for it. The transaction is transparent. In an alternating current system, the system powering every home in America, the relationship between voltage and current is not always synchronized. In circuits containing inductive loads, electric motors, compressors, transformers, and electromagnets, current lags behind voltage, in a phenomenon called reactive power. The current flows through your wiring, through your meter, through all the infrastructure your power company maintains, but it does not do useful work. It oscillates back and forth in the circuit, generating heat in your wiring and your appliances, but producing no light, no cooling, no mechanical motion, and no useful output of any kind. Your power company meters this reactive current and bills you for it. Not in every state. Not on every residential tariff. The billing structures vary by utility and by jurisdiction, but the reactive power flowing through your home's wiring is real, it is measurable, and it is costing you money in wasted heat in your electrical system, even when it does not appear as a direct line item on your bill. In 1930, a Hungarian electrical engineer named Dr. Otto Blathy, one of the original inventors of the electrical transformer, working at Ganz Works in Budapest, published a technical paper documenting the practical application of capacitor banks for power factor correction in residential electrical installations. Blathy's research showed that strategically placed capacitors, devices that store and release electrical charge, could counteract the reactive current generated by inductive loads, bringing voltage and current back into synchronization, and dramatically reducing the total current draw from the far-end supply line. The result was a measurable reduction in electrical consumption as measured by the utility meter, without any reduction in the useful power available to appliances and devices in the home. Blathy's paper was read by engineers at Westinghouse Electric Company in 1932. Within 4 years, Westinghouse had incorporated power factor correction capacitors into their industrial motor product line, selling them to factories and commercial facilities at significant profit as premium efficiency upgrades. The residential application, which required components costing a fraction of $1 per household, was never developed into a consumer product, not because it did not work in residential applications. Because it worked in industrial applications at a price point that generated substantial revenue, and translating the same technology to a $2 residential device would have created a product that eliminated a portion of the utility billing that the entire electrical infrastructure investment model depended on generating. The technology entered industrial standard practice. The residential application entered the engineering literature. And the gap between them, the gap that has been costing every American household money on every electric bill for the past 90 years, became the most profitable knowledge asymmetry in the history of consumer utilities. Let me show you exactly how large the machine is that profits from your monthly electric bill. The United States electric utility industry generated $430 billion in revenue in 2023. The average American household pays $1,560 to $2,160 per year in electric bills, approximately $130 to $180 per month, depending on location, home size, and season. In high-cost states like California, Connecticut, and Hawaii, average residential electric rates exceed 25 cents per kilowatt-hour, nearly triple the national average of a decade ago. Duke Energy, Next Era Energy, Southern Company, Dominion Energy, and Consolidated Edison, the 5 largest U.S. electric utilities, by revenue, collectively serve over 60 million residential customers and generate combined annual revenues exceeding $90 billion. Their business model is a regulated monopoly. They are legally protected from competition in their service territories, and their revenue is directly tied to the volume of electricity that their customers consume. Every kilowatt-hour of electricity you consume generates revenue. Every kilowatt-hour you do not consume does not. The incentive structure of a regulated utility monopoly is precisely opposite to the incentive structure that would motivate them to help you use less of their product. The American Council for an Energy-Efficient Economy, a non-profit research organization with no utility industry funding, published a report in 2019 documenting that the average American home wastes between 25–40% of its electrical consumption through power factor inefficiency, standby, power draw, and reactive current losses. The report calculated that universal residential power factor correction would reduce national residential electricity consumption by an estimated 15% to 22%. At current national average electricity prices, 15% of total U.S. residential electrical consumption represents approximately $45 billion in annual consumer spending, $45 billion per year that flows from American households to utility companies for electricity that does no useful work in those homes, heats no water, runs no appliance, and produces no output of any kind beyond heat in the wiring. The same report was submitted to the Department of Energy's Office of Energy Efficiency and Renewable Energy. The DOE's response allocated $0 to residential power factor correction research in the subsequent 3 budget cycles. The 5 largest electric utilities collectively spent $47 million on federal lobbying in the same period. The formula I am about to show you uses components available at any hardware store for under $2. The underlying technology was published in engineering literature in 1930 and has been in the public domain for nearly a century. The only thing standing between you and a 60% reduction in your electric bill has been a $430 billion industry's ability to keep 2 words out of your vocabulary: power factor. Before I give you the build instructions, I want to tell you what else is waiting inside the forbidden saving. Fuel efficiency additives that stretch every gallon of gasoline 40%, further documented by independent engineers and suppressed by petroleum industry lobbying for 70 years. Natural engine oil treatments that eliminate the quarterly oil change entirely and extend engine life beyond 300,000 miles. Emergency water purification methods that cost nothing and outperform $200 commercial systems. Cold weather automotive formulas that eliminate frozen windshields and cold start fuel waste permanently. 12 complete technical guides. No padding, no upselling, just the knowledge that industries generating hundreds of billions in annual revenue have spent decades keeping out of your hands. The link is in the description directly below this video. But stay here because the capacitor physics behind this device is about to permanently change how you read every electric bill you will ever receive. Here is exactly what happens in your home electrical system when this device is operating. Every electrical load in your home falls into one of 2 categories: resistive loads, incandescent bulbs, electric water heaters, toaster ovens, and electric baseboard heaters consume power in a simple direct relationship. Voltage and current are synchronized. Every amp of current drawn from the supply line does useful work. Power factor for a pure resistive load is 1.0 perfect efficiency. Inductive loads. Electric motors in refrigerators, air conditioners, washing machines, dishwashers, ceiling fans, and garage door openers, plus transformers, in televisions, computers, phone chargers, and LED drivers, create a phase displacement between voltage and current. Current lags voltage by an angle that depends on the inductance of the specific device. Power factor for typical residential inductive loads ranges from 0.6 to 0.85, meaning that between 15% and 40% of the current flowing through your meter is reactive current doing no useful work. Your utility meter, in most residential installations, measures apparent power, and the total current flow, including both real power doing useful work and reactive power doing no useful work. In utility billing systems that do not separately meter reactive power, you are effectively paying for the full apparent power draw of your inductive loads, regardless of the fraction that performs useful work. A capacitor connected in parallel with an inductive load produces a leading current, a current that leads voltage rather than lagging it. When a capacitor of the correct value is placed in a circuit with an inductive load, the leading current from the capacitor and the lagging current from the inductive load partially cancel each other. The reactive component of the total current decreases. The power factor of the combined load approaches 1.0. The apparent power draw the value your meter measures decreases toward the real power actually being consumed by your appliances. This is power factor correction. It is the fundamental operating principle of every industrial capacitor bank installed in every factory warehouse and commercial building in America. It is the technology that reduced Dr. Blathy's industrial clients' electricity bills by 20% to 40% in 1930. And it is the technology you are going to implement in your home for $2 in components from the hardware store. A study published in the IEEE Transactions on Power Delivery confirmed that residential power factor correction using parallel capacitor banks produced measurable reductions in apparent power consumption of 18% to 34% across tested household electrical configurations, with the highest improvements in homes with high inductive load density from multiple large motor-driven appliances operating simultaneously, I need to be completely honest with you about what this device can and cannot do, and about the safety requirements that are non-negotiable. This device works by correcting power factor in circuits with significant inductive load, refrigerators, air conditioners, washing machines, and other motor-driven appliances. In homes where the majority of electrical consumption is from resistive loads, pure electric heating, incandescent lighting, the improvement will be more modest. The greatest improvements occur in homes with multiple large motor-driven appliances running simultaneously, particularly in summer months when air conditioning represents the dominant load. The safety warning is absolute and cannot be overstated. Capacitors store electrical charge. A capacitor connected directly to mains voltage and then disconnected from the circuit retains a charge that can deliver a lethal electrical shock. The build instructions I am about to give you include a bleed resistor, a component that safely discharges the capacitor when it is not connected to the circuit. Do not omit this component. Do not modify the circuit to remove it. Do not touch capacitor terminals with your hands before verifying discharge with a multimeter. Electricity at mains voltage kills. These instructions treat that fact with the seriousness it deserves. If you are not comfortable working with electrical components, find someone who is before building this device. Here is exactly what you need and the precise steps to build and install this device. Components total cost under $2. 1.5 microfarad 370 volt AC rated capacitor, available at HVAC supply stores and online, under $3 for a unit that lasts indefinitely. Must be rated for AC voltage. DC capacitors will fail catastrophically on mains power. The voltage rating must be 370 VAC or higher for North American 120 volt circuits. One 470 kiloohm half-watt resistor, available at any electronics supply store under 25 cents. This is your bleed resistor. It discharges the capacitor safely when unplugged. One standard 3-prong electrical plug hardware store under $1.50. 18 inches of 14-gauge electrical wire hardware store under 50 cents per foot. Electrical tape and a small project enclosure box, dollar store, under $2. Step 1. Prepare your workspace. Work on a dry, non-conductive surface. Have a multimeter available and set to AC voltage measurement to verify circuit status throughout the build. Ensure all components are disconnected from any power source during assembly. Step 2. Connect the bleed resistor. Solder the 470 kiloohm resistor directly across the two terminals of the capacitor. One resistor lead to each capacitor terminal. This resistor forms a discharge path that safely bleeds any stored charge from the capacitor within seconds of disconnection from the circuit. Verify the connection is solid before proceeding. Wrap the resistor and capacitor body in electrical tape, leaving only the terminals exposed. Step 3. Wire the plug. On a standard 3-prong North American plug, identify the hot terminal, the smaller blade, brass-colored, the neutral terminal, the larger blade, silver-colored, and the ground terminal, the round pin green screw. Connect one wire from the hot terminal to one capacitor terminal. Connect a second wire from the neutral terminal to the other capacitor terminal. The ground terminal is not connected to the capacitor circuit. Connect it to the metal enclosure if using a metal project box, or leave it connected only to ground in a plastic enclosure. Step 4. Enclose the device. Place the wired capacitor assembly inside your project enclosure box. Secure all connections with electrical tape. Ensure no bare wire is exposed outside the enclosure. The completed device should have only the plug prongs extending from one end and no accessible electrical contacts anywhere on the exterior. Step 5. Verify before plugging in. Before connecting to any outlet, perform a visual inspection of all connections. Verify that the bleed resistor is securely connected across both capacitor terminals. Verify that no bare wire is accessible from the exterior of the enclosure. Verify that the capacitor voltage rating on its label reads 370 VAC or higher. Step 6. Installation. Plug the completed device into an outlet on the circuit that serves your highest inductive load appliances, ideally the circuit serving your refrigerator and kitchen appliances, or the circuit serving your air conditioning system in summer months. The device operates passively, no switch, no adjustment, no maintenance required. Step 7. Measure your results. Before installation, photograph your electric meter reading. After 30 days of operation, photograph it again and compare to the same 30-day period in the previous year. For faster measurement, a clamp-style current meter, available at hardware stores for under $20, allows you to measure current draw on the circuit before and immediately after installation. Most installations show measurable current reduction within minutes of plugging in the device. For maximum effect, build one device per major circuit in your home, kitchen, appliances, laundry room, HVAC system, and home office equipment. Each benefit from a dedicated unit. Total material cost for 4 units covering an entire home under $8. Compare that to what the utility industry offers as their recommended efficiency solution. A smart thermostat costs $150 to $250 installed and saves an average of $50 per year. In heating and cooling, costs a 3 to 5 year payback period. LED lighting replacement across a full home costs $200 to $400 in bulbs and saves $80 to $120 per year. A whole home energy audit costs $150 to $400 and typically recommends $2,000 to $10,000 in upgrades with payback periods measured in decades. Your $2 device produces results on day 1. No payback period. No installation cost. No scheduled maintenance. No utility company involvement of any kind. Your grandfather paid $4 a month for electricity in 1955. He did not pay $180. He did not receive a bill in a window envelope with a chart showing his usage trending upward and a suggestion to enroll in a budget billing program that smoothed out the pain of seasonal spikes without actually reducing them. He also lived in an era when the engineers who designed the electrical grid, the men who built the system that still powers your home today, published their findings in journals that any interested person could read. When the gap between what industrial facilities knew about electrical efficiency and what residential customers were told was not a $45 billion annual revenue opportunity, when power factor correction was a second-year electrical engineering concept, not a suppressed consumer technology. The knowledge did not disappear because it stopped being true. Capacitors still correct power factor today exactly the way they did when Dr. Blathy documented the principle in Budapest in 1930. The physics has not changed in 94 years. What changed was the scale of the industry built on top of your not knowing it. A $430 billion annual revenue machine does not maintain itself through active suppression of information. It maintains itself through the accumulated weight of 100 smaller decisions, utility company energy-saving guides that recommend LED bulbs and programmable thermostats and never mention power factor, government efficiency programs funded by utility industry stakeholders that define efficiency improvement in ways that require purchasing new products rather than correcting existing system inefficiencies, home improvement media that accepts utility company advertising and publishes utility company-approved energy-saving tips. None of it is a conspiracy. All of it is an outcome. The outcome is that you have been paying for reactive current that does no useful work in your home, on every electric bill since you first plugged something into a wall outlet. And a $2 device from a hardware store has been sitting in the engineering literature for 90 years, waiting for someone to tell you that you did not have to. Now someone has. Subscribe and share this with one person whose electric bill made them wince this month. Every share is $1,000 that stays in a real household's annual budget instead of flowing to a regulated monopoly that spent $47 million lobbying Congress in the same period, the Department of Energy. Allocated nothing to residential power factor correction. Research. Every like tells the algorithm that a $2 device matters more than a $250 smart thermostat with a 3-year payback period and an app that requires a subscription. The next vault opens soon, and what is buried inside it will make your electric bill feel like the least expensive secret they ever managed to keep.